Hello, everyone. Fantastic. Nice to see you here in Bangkok. And thank you for taking the time for this presentation. So let me first quickly set the stage before we go directly into the actual demos, because I think those are more interesting than just taking a look at prepared slides. Why do I stand here? Well, we created a proposal for the Treasury to basically fund a Oracle ecosystem initiative that all the parachains could start using and leveraging, instead of everyone just building their own thing. And Acurast is actually very, very strong in this use case, because the way that Acurast ensures verifiable computation is by leveraging a device that you're very familiar with and you have in your pockets, the mobile device. These little champions are actually quite amazing because they have a secure chip that secure down the entire mobile operating system, and they allow you to do something that is this verifiable compute. This verifiable compute comes into play mostly for as well Oracle use cases. It's quite handy because you can prove to the world that you did a handshake with the Binance server, and the Binance server then later on has provided you with a specific set of information. The whole thing is completely powered by mobile devices, and also allows for more performant compute. If you wonder how the other side looks like of the equation, it's basically this. These are pictures from the community that we have. People are now onboarding devices. It's very, very easy. It takes about 3 minutes to onboard a device, and then the device becomes a computing unit of the network and can no longer be used for things like calls. And this basically just dedicated to this single use case. If you want, you can always go back. You can just wipe the device. Now, you may wonder, why are people doing this? Well, because for starters, whoever is consuming their resources is paying for it. But the other thing is, now in this bootstrapping phase, there is part of the inflation of the Acurast network that is paid to whoever is heart beating and showing that they are available for this kind of compute. Cool. This was now the supply side of things. We'll jump right into the demand side of things, specifically with the Oracle use case. Now, let's assume that you're a developer and you want to start working with Acurast, you want to start developing with Acurast. What you're actually going to do is you'll be headed over to the Acurast console. This is console.acurast.com. Anyone can basically just go on that website. It's a dApp that talks directly to the Acurast parachain, and the Acurast parachain is the scheduling and orchestration layer of this decentralized cloud. We would, in this case, say, so this is how you're greeted. On one hand, you can start adding devices, which we're not going to do in this short amount of time. Happy to show you that at our booth. But the other thing, the other part of the equation is actually creating jobs. Now, you have to think of this as something that takes about 2 or 3 minutes of delay before your task starts running. And that's quite inconvenient if you actually are in the development phase, because you want to iterate quickly, see how your script is doing. The way you develop at the moment with Acurast is through JavaScript. It's a V8 engine that is provided to you. There is also a Node.js engine that has even more features and functionalities to it. But in this specific case, we're now taking a look at just the V8 engine. So you would head over to the Acurast console, say, I want to set up a new job. And the first thing you want to do is actually set up a live coder. To set up a live coder, you need to first deploy this snippet that is populated for you. And then you can say, OK, how long are you planning to develop this, because the resource will be allocated just to your use case for that time. Here we give it a delay of about 3 minutes to start, and say, okay, let's go for roughly an hour, and why not, let's have directly 4 devices allocated to this. I'm going to pay 0.1 CACU. What now happens is that I have to sign a transaction with my Polkadot.js, which you're not seeing because it's now showing on my other screen. Maybe I can show you that as well, just since you're probably familiar with this. I will remember now the password for the demo, and then we'll go back to our console here, and at some point the job will be picked up, and there will be now the matchers that are observing the blockchain and observing the resources that are available. And out of this pool of more than 1,000 devices, they will find 4 devices that are complying to the rules that I have defined. Now, for this use case, I'm not requiring any specific high security thing, so it's actually basically all the 1,000 devices would be eligible, and we see they already got matched. We have now 4 devices that have matched, and what we're waiting for is for them to acknowledge the job. So they get matched by the matcher, but then each and every device, this is by the way how the device looks when it's set up. It's fully locked down only to this specific purpose. The device will now say, hey, I'm ready. Fine, let's go. I'll take on this task. And here you see they actually have acknowledged all 4, and the next phase would be to actually start with the job. Now, we're not going to wait here just for those 3 minutes to start. I've set up the live coder beforehand and have it here. That's maybe also interesting to know. If we are now going to the job section, we'll see, okay, this is assigned, ready to go, but not in progress. Only the other one here is in progress. And what we see here are the identities of the processors. So each and every processor receives its own identity with a private public key that is dedicated and stored inside the secure enclave of the mobile device. And you can talk to them directly through WebSockets, because we opened up this channel before. So now we copy that and can then basically just add here this to the list of our processors. One is already running, the other one is not running. That's why we're currently taking the one that is running and just testing whether this actually worked out. And we'll pray to the demo god and see if now our live coder, yes. So you see the processor, that is processor somewhere distributed around the globe, is reacting to the things that I'm asking it to do. In this case, I'm asking it to just print the word test. You can also do some calculations in there, and yeah. But this is not a really interesting use case. I think what is more interesting is the Oracle use case in this case. And for that, I will have to show the, here we go. All right, there is an example of an Oracle use case that is on GitHub. You can take a look. It's an EVM Oracle in this case. We're going to be deploying this EVM Oracle, and I loaded it already on the Remix Ethereum IDE, and the chain that we're using for this case is a test chain provided by Tanzi that has an RPC, and they were kind enough to fund me with some faucet tokens. The dummy oracle that you see here is a Solidity contract which implements the Chainlink aggregate v2, v3 interface. This means it's fully compatible with anything and everything that is compatible with Chainlink. It is, however, a very, very naive implementation. You cannot use this just for your production oracle because, as you can see here, anyone is allowed to set the price. You would want to actually verify that only a certain sender, namely the processor with its key that is inside the secure enclave, is capable of signing. But for demo purposes, I will just use this. You have here a couple of things like the interface from Chainlink with the latest answer, latest timestamp, latest round, and so on and so forth. Though it will fully work with a fork of Aave because they're using the Chainlink oracle, and we're going to deploy that. And why not? Let's deploy it for dot against USD T. And here we go. No, that was the wrong one. Okay, just fine. So I'm going to deploy this. This will now take some time for it to be deployed for the next. Here we go. All right, I deployed this earlier on, so we could already start. Yes, of course, it's asking me to confirm here as well with MetaMask the transaction, which I'm doing right now. And then we'll see it deployed shortly here. All right, so while we're waiting, what we can take a look is at the counterpiece, which is the Oracle script, which is the script that we're going to use here in this case. We have that Oracle job in two formats. We're going to take this one. Now, one of the things that you will see here is that we're actually doing the certificate pinning of the Binance server. So what you see here is the public key that they're using for their certificate for the TLS handshake. And you can find that out pretty easily by just opening up a session with Binance and then ask it, hey, please show me the details of the certificate, and then you will see here the public key that is being used. And this ensures that you're actually talking to the Binance server and there is no one in the middle tampering with your data. So we can copy this and move it over to this one. It will be the same, so yeah. All right. Here we define the destination contract. In this case, we'll take the one that we just deployed. By now, we see that this one worked. We also see that the latest answer at the moment on chain is returning 0. And yeah, we'll just copy that into our Acurast console over here and replace this old one. What we're also going to do is, we're not interested in the Bitcoin against USDT. We're interested in DOT against USDT. And for the rest, we can keep it the way it is. Now, we can choose our loyal worker. And what we see here is that it's fetching the price. It successfully managed to fetch the price. But it's saying, hey, I don't have enough money to publish the price on chain. So that's fine. We can solve that. We'll see here, this is the 038. We'll go to the jobs. And then it's, I believe, this one. Here we get all the details of the various chains that are supported, of the various, like the various addresses that this processor is generating. And then we'll take that and go and fund it with MetaMask by sending it one Tango. And we'll confirm that transaction as well. All right. So we can see here we are still, latest answer is still 0 because we have not published the price yet. And probably if we now try again, let's see. It ran through pretty quickly. And maybe we'll get a transaction hash if, yes, fantastic. Now we actually have a transaction hash. This means that the processor was fulfilling on-chain with the address that is specified. Okay, this is not showing us that, but that's fine. What we can check here is now whether the latest answer got updated. So not yet, which probably explains why we cannot see it here yet. Ah, fantastic. Now we see also the transaction that is pushing the data on-chain, and we'll be able to, not this one, we were over here. Yes. Check out the latest answer, and we see that it's 10.4 because we have specified up here 6 decimals. Depending on whatever you're observing, you will want to adapt that. Now, prices, of course, are super interesting for DeFi use cases, but you can, you're super flexible. You can also take a look at Wikipedia and then maybe observe the outcome of a soccer game and take Wikipedia as the oracle of choice. You're super flexible on what you wanna and can do with this. Now, how flexible are you actually? Well, you can run everything that you're able to run on AWS Lambda with this setup, and it's not only cheaper and it's not only decentralized, but it's actually also 34% faster for certain tasks. Okay, so if the tasks are CPU intensive, CPU and memory intensive, then it will be faster because it is nearer to the actual CPU, to the actual core. And it's actually remarkably faster compared to Azure, where it is even twice as fast in that case. Now I've shown you the EVM oracles. Let me get my mouse back here. There is, now this oracle, the way you've seen it, what we can do is say, okay, we now tested our code, it works as intended, we're ready to go. Let's say that we want some redundancy, and let's say that we want this to be updated at a fairly quick interval. We'll say, okay, let's say we start at 30, we run for 2 hours, and we have an interval of 1 minute. So this will be a total of 107 execution. The actual duration, because we are consuming an external service, let's give it 2 seconds. And then why not, let's go for 12 processors and pay them some rewards. That's a little bit too much. Sure, let's go. And here again, it will show me on my screen here to sign the transaction, which I'm going to do now, not showing you that, and publish the job on-chain so that others can start going for it and accept this job. After they accepted the job, half past, they will start every minute to publish the new prices. Another thing that I want to show you on the screen, so we can keep this one open to see that they're actually getting matched. Another thing that I want to show you is you have the ability to share secrets with the processors. So if you have an API key and you're the one paying for the data feed, I don't know, like gold prices or any price that is not readily available, or even if you want to have a Twitter bot that is fully controlled by an Acurast processor, you can type in the API key directly here as a key value pair and reuse it in the environment that we've shown before. The value here is shared only with this device, okay? Because it is fully encrypted with a key that only this device in the secure enclave is then capable of decrypting afterwards. That can come in handy for private sorts of APIs. So we see here it got matched, 12 have matched, 11 have answered, and probably by the time we're over time, we'll be able to match the rest. Cool. So we've shown you now how to set up an oracle that iteratively every minute will be publishing prices. What else can you do? Well, you have a WebSocket connection that you can leverage directly to the processor. This means that you will be able to also create on-demand prices. So ask on demand for an observation that then should be published directly by the user on chain. Okay, so it's not you that has to pay for the fee. If you're interested in that, there is a snippet up here where you say on-demand access. These are the proxies that are distributed that allow you for those kind of connections. And then based on the payload that you give it, you can request for a specific different answer. All right. I see that this is taking some time to load. That's fine. And because I'm almost through, and I see that I'm also quite on time there, okay. Yes, let's see if this still loads. But you can imagine, basically based on this live coder, because the live coder is also using the sessions, the WebSocket sessions, you can then basically just ask, hey, please sign me this observation so that I can bring it back on-chain on the other side. From a compatibility perspective, we do have full EVM support that you've seen here. You don't need to be integrated as a chain. You just pop in your RPC and off you go. The other thing that we offer is as well a palette that allows you to integrate this in your substrate-based chain. And also ink support, which now is also unsure how further maintained that will be. Cool. And that's it from my side. See that this one is still loading, but whoever is interested in that case can also come over at our booth, and then I'll be happy to show you more details on that side. And yeah, join the cloud revolution. And if you have any questions, I'm open for questions.
So you mentioned that if we have a private API key, we can submit that and it will be encrypted, but the device that takes the job can, of course, decrypt it.
Yes.
So in theory, if they inspect the packages, like web packages, like a tool with Wireshark, they will be able to steal our keys?
They won't, because you do a TLS connection together with the server before you pass in the get parameters. So you've seen the public key of Binance. What ends up happening is that whoever is inspecting with Wireshark will just see the encrypted stream and never see the actual API keys that are being exchanged.
Okay, so maybe with some another reverse engineering tool, they can decrypt the message, because it's kind of it has to be decrypted in the end device, which is like not ours, right?
This end device is not yours. It's someone else's that is setting up and offering this to you. It's leveraging the key store of this device. Not even whoever has full access over the device is capable of accessing any of that data. Because if you take a look here, you won't be able to debug anything. It's fully locked down only to that purpose, even if you start plugging in something. Even with memory inspection, like, you're not able to actually decrypt that.
Thank you very much.
Cool.